Hi, this is the second video in the series on exponential models. The first video was introducing the exponential models and also worked through a series of examples trying to demonstrate some of the different types of questions you can ask about an exponential model. In this discussion here, I'm going to talk about half-life models, and a little bit about doubling time models. These are reformulations of the exponential model, which make it easier for us to work with them outside of the world of mathematics. The third video in the series will be concerned with the Newton cooling process and also some financial models. The next example is concerned with a research technique known as carbon dating. The technique of carbon dating works as follows. When plants are alive, they take CO2 from the atmosphere and use photosynthesis to bind it into larger carbon-based compounds within the plant. A certain small fraction of the carbon in the atmosphere is a radioactive isotope of carbon, carbon-14. Most of it is the normal carbon-12. And as the plant incorporates a small amount of carbon-14 into its chemical compounds, that leaves itself as a signature that we can read years later. Because when the plant dies, it stops incorporating C14, and now we have a fixed ratio of radioactive carbon to non-radioactive carbon in this plant material. If we come back many centuries later, we will find that the carbon-14 is decomposed, but the rest of the carbon is stable and is still there. So the amount of carbon-14, in fact, it'll be the ratio we measure, will have gone down by a radioactive decomposition process. Well, here's an example. A sample of wood is taken from the center post of an old building in Suffolk, England. It is estimated that this sample now has 89% of its original radioactive carbon-14 content. If the half-life of carbon-14 is 5,700 years, what is the expected age of the sample? And as a check on your calculations, you can use the knowledge that archaeologists believe that the center post is at least 925 years old. Now that's probably because they have some documents that mention the center post, and they know the age of those documents. Okay, let's solve our problem. Let C0 be the amount of carbon-14 at time 0. When the wood was growing as a tree. Let C of t be the amount of carbon-14 at a later time, t. The half-life formula is C of t is C0 1/2 to the t over lambda, and lambda is the half-life, which we know is 5,700 years in our case. So our problem says that Ct over C0 is equal to 89%. And so from this, we're trying to solve for t. So C of t over C of 0 is 1/2 to the t over 5,700. That's the formula for the half-life process. And for the t we're interested in, that number is actually 0.89. Now we have to solve for t, so we take logarithms. We get t over 5,700 times log 0.5 equals log 0.89. And then t is going to be 5,700 times the ratio of the two logarithms, and t turns out to be 958.3 from this calculation. And you'll remember that the archaeologists had already told us that they thought it was at least 925 years old, and we have got from our calculation, we're going to claim it's about 958 years old. So that's a comfort. We really got compatible answers there. Problem 3 is a rather it's a chestnut. This same problem occurs in many calculus books, and it goes as follows. In 1953, carbon-14 dating was used to calculate the age of a painting attributed to a painter, Vermeer, who lived from 1632 to 1675. And we're given that 99.5% of the original carbon-14 is still there, and we're asked to do a carbon-14 dating to see whether this painting is actually a forgery. This calculation was used in a legal case about the claim that this painting was a forgery. I should note that in fact there were other radioactive decompositions processes that were used in the dating of that particular painting, which were more important than the carbon-14. And if you just Google Vermeer carbon-14, you will get thousands of hits that are about this problem. I'm going to go on and solve a different one.